Okay, so our next speaker is Malhar, and he will speak about broadcast channel synthesis.
Okay, thanks, Pavel. So this is based on my master's thesis under first I'll introduce the problem and we will look at some prior work also, and then I will show our result, and I'll give some sketch of the proof of achievability for upper bound. For lower bound, there's also a proof, but I don't think you'll have time for it. And if you have time, I'll show one example. So, first the introduction. So, what is channel synthesis? So, Claude Shannon studied the problem of channel coding. That is, given a noisy channel, you want to reliably send messages over it. So, after you are doing this coding scheme, you can send reliable information over. Here we are considering the opposite problem. That is, you are given a reliable link and also some common randomness, and you want to simulate a noisy channel. So you want to observe some input and produce some output, so that to an outside observer it looks like some channel Q of y given x. So this is the problem that we studied, and this is the basic example of that. So to be more precise, we say that we want to consider the rate of messages. So basically what this processor will do is that it will look at a sequence of, it will look at an XN sequence, and it will look at the value of this shared randomness, and it will use some randomized function to generate a message. And P2 will look at the message and the shared randomness, and then it will have its own randomized decoding function to generate y.
Just why can't you eliminate P1?
So you will need to communicate many bits if you want to. So you would need entropy of y bits per.
But then don't have to capture that in process. You have to reduce that
Yeah. So you will increase the rate of theta if you, but we are interested in, this is reducing this is more important than this theta. So
that's one time analysis.
Yeah. So this is not one shot setting. We have multiple sequences. We have long block. So in fact, we have asymptotically infinite block. So we have these randomized functions, and we want to say that so this P of x and y n, this is the distribution induced by these encoders and decoders, and qx times qy, this is the prescribed distribution, the demanded distribution. That is the thing that we are supposed to produce. And we want to say that the total variation distance between them goes to 0 as the block length tends to infinity. So this is the asymptotically vanishing error. So you can also study the one shot or finite block length setting, but we won't go into that here. And also we have R opt is the minimum rate of communication requirement. So we don't care how much randomness we use. We just want these two together to be achievable. So that is the optimal. So we will look at classic result. So this is for this particular channel. So if you want to simulate this q y given x, and you are also given the input distribution qx, then you have to. So you can find some random variable u such that it splits X and Y. So X, U, Y is a Markov chain. Conditioned on U, X and Y are independent. Then the minimum communication rate is mutual information of X and Y. And in general, you have this rate reading. So that's not so important to want to say about this. And this is interesting because the capacity of this channel is also mutual information of X and Y with this input. So if you were consider the original channels problem and you were to use this channel to send some information, then you would get this rate at which you can send information. And it turns out that to simulate the channel also, you need the same rate. So there is another related work, which is due to Gautam Kurri, and he studied a coordination problem, which it looks sort of different. So now you don't have any information being sent. There's no incoming random variable, but P2 and P3 are supposed to produce YN and ZN sequences, which have to be correlated in some predefined fashion. And P1 is just there to provide coordination between those two, because without P1, they don't have any common information. And also, we have now two shared randomness variables. So theta1 is shared between only P1 and P2, and theta2 is shared only between P1 and P3. And using this, they want to create this joint distribution. And for this, optimal rate was shown to be max of two things. This one is the so you want to again select some P, U, Y, and Z. And sorry, I forgot to write it, but Y and yeah, so you have to select some P, U, Y, Z, and it will the communication rate would be mutual information between Y, Z conditioned on U, or this one, which is
So U is like
so U is basically what message you are sending. It represents
Ah,
the message that you are sending. So I will describe our work. So it is a common generalization of both of these things. So we now have an input and two outputs, and Xn is coming in at distributed according to some Qx. And these theta1 and theta2 are independent shared random variables. Theta1 is known to P1 and P2. Theta2 is known to P1 and P3. And they are supposed to produce this Yn and Zn sequence according to prescribed distribution. And notice that if Z were independent of X and Y, then P3 has no role, and P3 can just use private randomness to produce Zn. And P1 and P2 are now playing the Paul Cuff's game. They are doing this channel simulation. Similarly, if X is not present, if X is independent, if Y and Z are independent of X, then we just get the previous Fourier task problem. And for this problem, so one more observation is that if instead of this we had common randomness which was known to all three players, then the fact that P2 and P3 are actually different processors doesn't matter anymore. So it is as if you are taking an X and producing joint variable YZ, Y, Z. So this is actually important to use this trick in our solution.
So P2 and there's no communication happening between P2 and P3 at all. So
No.
P1 is sending the same message to both P2 and P3.
Yes.
And they are going to decode it possibly different.
Yeah.
So
So our result, we have this, we have a upper bound and a lower bound, And there is some gap between them. You can see that here V and W are replaced with Y and Z. So unfortunately, we don't have a tight one. But in all these special cases, that is, these two special cases, our result reduces correctly to the corresponding results that been shown before. And
What is the role of P and W?
so here, in this case, U is the information that is known to all three processors, and V is information that is known to P2 but not by P3, and W is something that is known to P3 but not to P2. And so you have to choose a distribution in such a way that Y is so there are some conditions on this that conditioned on U and V, Y should be independent of everything else. So that is because in practice, what is going to happen is that X will use, so P1 will look at these variables that he has, and he will send some message to both of them, and P2 will decode U and V, and P3 will decode U and W. So Xn looking at his variables will generate some U, V, and W, and he will send information so that P2 can decode U and V, P3 can decode U and W, and then based on their decoded things, they will use private randomness to generate the Y and Z sequences. So this distribution that you choose has to satisfy those constraints that conditioned on U and V, Y should be independent of everything else, so that the distribution that it generates is correct. And similarly, conditioned on U and W, Z should be independent of everything else. And conditioned on all three things, U, V, W, X and Y, Z should be independent. And so I will now we will look at the proof. So before we look at the proof, we look at I'll show you the proof of the simple version. So since we are dealing with asymptotics, we only care about the typical sequences. So that is the set of sequences which form a very high probability set. So for example, if you have sequences of like Bernoulli P sequences, then these would be all sequences which have Hamming weight P, Hamming weight n times P approximately. So what we're going to do is we are going to take all Yn sequences and we are going to assign uniformly assign to them a string of length R plus R1. And so something like this. And what is going to happen is that this part of the string will be taken from the randomness that is available, and this part of the string will be decided by P1 and sent across as a message. And using this entire string, the processor at the end will go, decode what Y should be and output that, what Yn sequence should be, and output that sequence. So what are the conditions for this succeeding? So the constraints are that at most one typical sequence should be in each correspond to each bin or each string. So for this we need that the number of strings is number of n bits, the bit length of the string is more than the entropy of Y. So number of typical sequences is 2 to the n times h of Y. And the number of strings is 2 to the n times R plus R1. So if this condition holds, there will be exponentially more sequences than there are n bit Y strings. So then you would be able to pick out, knowing the string, you would be able to pick out the correct Yn sequence. And the other constraint is that theta should be independent of Xn. That is because theta is not selected by you. So the first part of this string, so this part of the string is not selected by you, it is selected by the common randomness which is just given to you. So no matter what common randomness is given, you should be able to have some sequence which is consistent with the X that you see. So for this, we need that this rate has to be bounded by entropy of Y given X. So the reason for this is that given a particular sequence X, number of sequences Y which are jointly typical with it is at most 2 to the n times this. So if the rate of this is smaller than that, then we will be able to find, so given any string, we will be able to find a lot of, at least one yn sequence which is consistent. So we will be able to complete we will be able to complete this in a proper way, which is consistent with the extension. So with combining those two, we get that this communication rate is at least the mutual communication. So this is the optimal communication rate for this problem. So we have the, so I'm not showing the lower bound here, it is only the upper bound. So we can, yeah, so I will skip this part. So this is a more general version. So so here we are just doing this winning thing on the variable y. But in general, there's no reason why you have to select just y itself. You have some x, and you can send some u variable to it, such that xy is a Markov. And then at the other end, P2 can decode u and generate y using private randomness. So you are using u to offload some of the generation process to private randomness. So with this, you again do the same thing. You assign some sequence to un. Here we have this extra additional bit of things. This RF. These are the free bits. That is, it doesn't matter what you set them to, it won't change your XY distribution. So this is just to provide some slack to make it easier to analyze it. Then eventually we'll just set all of them to 0. So again, the constraints are so at most 1 UN per bin. So the total length of the sequence has to be entropy of U, and you have that theta and F have to be independent of Xn, and F has to be independent of Fn. So you get some constraints in that, and if you combine these constraints, you will get this one, which is Poisson. So we will just use an extension of this for our problem. So we have this problem, and X will generate, based on looking at X, you will generate some U, V, and W. P2 will decode UV and generate some Y. P3 will decode UW and generate some Z. So for U sequences, we will have some indices. For U and Pn sequences, we have some indices, and U and Wn sequences, we have some indices. And here we are, so again, we have some free bits. So F1 and F2 are all the free bits, which will be set to 0. This B1 is actually random shared randomness theta1. It is coming from there. B2 is coming from this theta2. And this M0, this is actually coming from common randomness. So actually you can use a trick to create some common randomness. So let's say you want to have some common randomness between all three processors. Let's say you want M0 bits of it. So what you can do is you can take M0 by 2 bits from here, M0 by 2 bits from here, and take an XOR and send it as a message. Then P2 can take M XOR theta1 to get theta2, and he can take XOR of these two to get theta1. So all of them now have M0 bits of common randomness. So you use M0 bits of common randomness, and in addition, you also have some message and some more shared randomness that you use. So the total shared randomness you use would be this one plus half of this, or this one plus half of this. So theta1 would be this one plus half of this. Theta2 would be this plus half of that, and the message rate would be Rn plus half of this. And again, we will have the same conditions that, okay, looking at theta1 and theta2, you need to be able to generate UVW which are consistent with it. So we have all these constraints. So I will just and pass them quickly. So you have a lot of constraints and a bit of tedious algebra is required to combine them all together. And this is, and eventually you get some kind of result like this. So don't worry about these. We anyway don't care what randomness rate we have arbitrarily enough. So just these two things that will show you the. So that will give you R is max of this and half of that. That is the result that we have. So I'm not showing the important bit today. And so in the last 2 minutes, we can see an example. So for example, this is a channel which we might want to select. So X is generated uniformly random. And this is a binary eraser channel. So with probability P, it will erase the 0 or 1 into some spots. And this sequence is further degrades with a eraser channel of probability Q1 and a eraser channel of probability Q2. So to produce Y and Z. So when both Y and Z are unerased, they have to agree, they have to have the same bit. And the fraction of places where both of them are erased also has to be correct. So this kind of thing you want to do. And so the simplest way to achieve it was obviously to just send the entire sequence. That is using n bits. That's not very fun. So another thing you can do is you can use this shared randomness theta1 and theta2 to decide the erasure pattern for these two channels. So that way now the processor knows when these two, which places are erased by these two. And you can also use your common randomness trick to generate a sequence, an erasure pattern for this channel. So that way all three processors know which locations are erased by this. So that way P2 knows the erasure pattern for these two, P3 knows the erasure pattern for these two, and P1 knows the erasure pattern for all three things. So P1 can just send the unerased bits. Those bits which are not erased by both Y and Z, that will be 1 minus P times 1 minus Q1, Q2. He will just send that many bits and plus some few extra bits for the generating the common randomness. And that will be the, so obviously the unerased bits you have to send, there's no way getting around it. So you cannot do better than this. And in this scheme I described, we had this unerased bits plus a little bit more to generate common randomness. So we had half of HP bits to generate common randomness, but you can actually do a little bit better. And the reason for this is that after you've generated these two sequences already, you have some locations where Y and Z are both been erased. And this fraction of those sequences have to also be erased by this thing. But which fraction you select, it doesn't matter. So you don't need to expand common randomness or anything to generate that. You just arbitrarily select it. So this saves some few bits. So that is the way to get. Yeah, so thank you.
Any question? Thanks, Malhar, again.